on that one. So my talk today is to give you a flavour really of a large field campaign. It's something that I did a couple of years ago. I led a campaign to Darwin in Australia. I was there for about 4 months during the wet season, and therefore got wet. And the campaign was to look at aerosol and chemical transport in tropical convection. And this whole project is coming to an end now, and it seemed an appropriate thing to try and summarise the results from it. So when Paul asked me for a title, I thought, oh, this would be a good title to give for a presidential address. And when I actually started summarising the results from this project, I realised there were far more than you could possibly get at the time available. So I should say selected results from the active project. So I shall try and explain to you a little bit in the next 40-45 minutes of why people like me get paid to go and do exciting things the other side of the world. I think Richard had to pay to do what he did, so I did slightly better there. Okay, so the focus of our experiment was on the tropical tropopause layer. So this used to be called the upper tropical troposphere. This diagram, which is a sort of, this is a rather nice version of a very traditional diagram. It's tropics here and the poles here, so this is a latitude cross-section, a height cross-section. This is the tropopause, or schematic of the tropopause here. And the idea basically is that this region here in the tropics, above where most of the convective outflow is, but below the cold point, is a rather unusual part of the atmosphere. And in that, it's not coupled very strongly to the rest of the atmosphere. And its composition is very important because the air that gets into the stratosphere, into the Brood-Hobson circulation, comes through here. And so whatever you've got here determines the composition of the global stratosphere. Well, that was one of the main reasons we went to look here. And also, of course, if you put clouds into this region, it's very cold, very high and cold. So if you manage to get clouds in there, then they will have a big effect on the Earth's radiation budget. So there was two sides to this campaign. We were looking at some cloud physics, and we were looking at some composition. And we were basically looking at the way that isolated deep convection in particular was lifting material into the tropical troposphere, into the TTL. And these are the basic problems that we try to address. And I'm going to try and answer these questions. How does air get to the tropical tropopause layer? Well, clearly it gets there by convection largely. But is that dominated by local transport or by transport from elsewhere? In other words, is it largely by larger scales or by local convective transport? And that was one of the main questions we were trying to answer. And we also want to know what's the partitioning between these sources. There's not a great deal known about aerosol getting into the tropical tropopause layer. Now, aerosol is important because cloud seeds on aerosol, and therefore, if you change the aerosol balance of this part of the atmosphere, you'll change the clouds. So it's important to understand how aerosol gets there. And as I shall show you, it's not a simple matter of transport in the case of aerosol. It's actually well more complicated than that. And then we wanted to know how does aerosol, not the aerosol in the TTL, but the aerosol in the boundary layer affect the development of convective storms. In other words, does this transport depend on what you put in at the bottom? In other words, how does pollution, the aerosol is associated with pollution, how is that affecting the development of this deep convection, if at all? So that was the kind of sort of things that we were going there to look at. This was in fact a very large international campaign. There are lots of other acronyms down here, for those of you that like acronyms. I'm not going to explain them. Basically, there was a big European consortium, particularly concentrating on the upper part of the TTL, and there was a large American and Australian consortium, and they were looking particularly at cloud processes. For those of you that work in universities, this was a consortium grant between Manchester, York and Cambridge, on the UK-led active side, but we also had lots of international partners in active from Germany and from America and from Canada. So it was we ourselves were an international consortium, and then all of these things were also a large international experiment. So lots of people. Fortunately, Darwin is an excellent place to go and do this sort of experiment. It's a first world city in the tropics. There are not many first world cities in the tropics. There's probably 2, and they're both in Australia. It had the infrastructure. We were based on the Air Force Base in Australia. Australia doesn't get invaded very often. It did in the Second World War, and so they maintain a huge Air Force Base in Darwin. Don't have a lot to do though. So they're quite keen to see scientists come there and try and use their Air Force Base. Prudently, the Australians keep all their Air Force back down south, because the unfortunate episode in the Second World War when the Japanese bombed them all because they were based in Darwin. So there's not much happening on the Air Force Base, which is good. Okay, so a little bit about the meteorology of Darwin. Right, so these are 2 nice, colourful satellite pictures. The satellite pictures, they're both from the wet season in Australia. They basically show you 2 extremes. So this is the Australian coast here. Darwin is more or less where my pointer is, so shown on the other diagram. And I'd just like to point out these islands to the north of Australia, which featured strongly in our campaign. These are the Tiwi Islands, Bathurst and Melville they used to be called, but it's politically incorrect to call them that now, so they're called the Tiwi Islands. They are populated by Aboriginal tribes. In fact, they're a kind of reservation up there. So we never set foot on the Tiwi Islands. We were discouraged from setting foot up there, and we just flew over them with our aircraft. This picture on the left-hand side shows conditions in the early part of the wet season. This is on the 1st of November. And during this period, you have this storm here called Hector, which blows up on these islands every day. So every day, about mid-afternoon, up goes a big thunderstorm. And you can see on the mainland, there's lots of these thunderstorms as well. So this was in fact, a very quiet day. You can see there's not a lot of convection anywhere here. The main warm pool is up here at that time. But in January, this is on the 17th of January, you can see the opposite. The whole thing is covered in cloud. And what's happened here is that the monsoon has set in over the northern Australia. You've got widespread oceanic convection going on here. There's convection everywhere. It's not just on land. And so, whereas here, you've generally got easterly winds coming off Queensland over this top end of Australia. Here, you've got northwesterlies coming out of the warm pool. And one of the things we wanted to do is contrast these 2 meteorological regimes, and we were fortunate we were actually able to do that. It's not always that these monsoon events don't last very long. They're associated with the passage of the Madden-Julian oscillation, gives you this enormous amount of rainfall in a few days, and then it all goes back to this again for probably another month, 6 weeks, and the whole cycle starts again. Okay, so you probably get about 3 of these pulses in a typical wet season. Oops, what am I doing? I managed to press the wrong button, sorry.